Our next speaker is Dr. Ouellette. She's a specialist in galaxy clusters and other things. She's also the public outreach scientist for Canada for the James Webb Space Telescope. And that's what she's going to talk about.
So thanks so much for inviting me. I want to thank the organizers for thinking of James Webb and thinking of me specifically. There are so many great people on this mission, and the fact that they asked me to do it is really an honor. I have a great relationship with RASC, and I have for a long time. I recently started some projects with RASC in Montreal for the first time, but really I need to give a special mention to RASC Kingston, who really got me started in doing outreach. I did my PhD at Queen's, and instead of being a TA, I was the Queen's Observatory Coordinator, and every single month they were there at the open house helping us out, and we often talk about astronomy turning kids into scientists. Well, the RASC turned an astronomer into a science communicator. So I think that was really fantastic. So round of applause for RASC Kingston. I need to thank them. Yeah. All right, so when we think about astronomy, especially all the wonderful work that you do, we think about a very sort of visceral connection, what we feel when we go outside, look at the skies, and this is something that we've been able to do in astronomy for thousands of years. Astronomy is basically considered the oldest science, but we've made leaps and bounds since then in how we look at the sky. And I'd say that the Hubble Space Telescope is probably one of the things that put us on the map for almost everyone in the world. Not everyone necessarily cares about astronomy, but everyone has seen a Hubble Space Telescope picture and has felt something when they saw that. So I think Hubble is a really major point in the history of astronomy in terms of the public's appreciation of it. And it has made so many different iconic images that we can refer to now. And one of the really awesome things that Hubble did also is tell us how big the universe actually was. So the Hubble Ultra Deep Field, which is the animation that you can see here, I'm sure you all know what it's about, but just to recap, it basically stared at a piece of the sky for a very, very long time, for several days, long exposure, in order to see lots of galaxies that we didn't know existed before. And most of these galaxies, they're very, very far away, so it sort of blew our mind when we realized that there is over 1 trillion galaxies in the known universe, and that number is getting bigger and bigger as we're able to peer further and further out. But unfortunately, Hubble won't be able to last forever. It's been up there for almost 3 decades now. It's nearly as old as I am. And I know, you're all like, oh, she's so young, right? And it has had the benefit of being serviced and repaired over the years. So you can see in this image here, we've had a lot of astronaut missions who have upgraded it, who have made it better. But eventually, and we can already sort of see it happening, the gyros are failing on Hubble. We're not able to do everything that we can. And even though it's still really a fantastic telescope with lots of great instruments, it's going to be surpassed eventually by some newer missions. And one of the really exciting missions that is going to be doing that, not replacing it, but successing it, its successor, we say, is the James Webb Space Telescope. And one of the key things that's different about James Webb, specifically for us, everyone in this room, or nearly everyone in this room, is that it has a Canadian contribution. It's a collaboration between 3 different space agencies, NASA, of course, the European Space Agency, but the Canadian Space Agency as well. And Hubble did not have that Canadian component. So of course the Canadian public got to benefit everything, all of the wonderful science that came out of Hubble, but we didn't necessarily have that sense of pride, like, oh yeah, we made this instrument and this is part of our astronomical heritage. Well, James Webb is going to change all of that. And that's really wonderful because hopefully this builds momentum with the Canadian astronomical community and puts us on the map for future space astronomy telescopes and missions. So there are lots of different differences between Hubble and Webb, not just the Canadian contribution. One of the important ones, unfortunately, is that it's going to be much further away from Earth than Hubble. Hubble is in low Earth orbit, which is why it was repairable and serviceable by astronaut missions. Webb is going to be an infrared telescope, however. Infrared being not the visible wavelength. Humans glow quite brightly in the infrared. Animals, the Earth, the moon, it all glows pretty brightly in the infrared, and that is all going to be noise for the James Webb Space Telescope, so we need to put it a lot further out. So it's going to be 1.5 million kilometers away from Earth. We're not currently able to send astronauts that far. Maybe one day we will. That might be one of the uses of the Lunar Gateway for astronomers, if we can use it as a sort of port for servicing space telescopes, but we're not there yet, and it won't happen during the lifetime of Webb, unfortunately. So this is why there's lots of jokes all the time about how Webb, it'll never launch, or it'll launch after we all retire, or something like that, even after I retire. But we need to make sure that it works before we send it up there, because if it breaks, we can't repair it. So that is one of the key things, but there's a reason why we're putting it so far away. It's because it's an infrared space telescope. Another key difference is the size of its mirror. So the Hubble Space Telescope has a 2.4 mirror aperture, and Webb is going to have a 6.5 meter mirror. So it's going to be a lot bigger. The collecting area is even, bigger because you square it. And it'll be, it's the first time that we have an open telescope. So that's a little bit scary because, some people imagine space is full of these space rocks careening all over the place, and they're like, oh my God, this $10 billion project is going to get, bombarded by all of these space rocks. But we know that there aren't that many space rocks. But it is going to be an open telescope. And the reason why it's open is because we don't want heat to accumulate inside the tube the way that it might in a tube like Hubble, because we don't want to contaminate the data that's being taken by this infrared telescope. Another reason why we need to make special considerations for it being infrared is the sun can also be a really big damper, because the sun can heat up the instruments on the Webb telescope. So we need to protect the instruments from the heat of the sun. And to do that, we made sure to build a 5-layer sun shield made out of mylar, and we always orient the telescope such that the mirror and the instruments are facing away from the sun, and they're being shielded from the sun by this 5-layer mylar sun shield. So we're making sure that the instruments are cooled so that they don't themselves glow brightly in the infrared and contaminate the images that are being taken. So you can see here in the diagram, you see that the temperature difference between the hot side and the cool side are very, very drastic. There are 4 different instruments, which I'll mention a little bit later on. 3 are in the near infrared, 1 is in the mid infrared, and the mid infrared one will also have a cooling system in and of itself to try and really stay cool so it doesn't glow in the mid infrared. Another really exciting but scary thing about James Webb is that it is so large that it will need to be folded up like origami in order to fit inside the rocket that will be sending it up into space. So one of the key contributions from the European Space Agency is going to be an Ariane 5 rocket that's going to be launching from Kourou in Guyana, and it's going to send the telescope up and reach eventually 1.5 million kilometers away from Earth, but the telescope itself, in its fully deployed mode, doesn't fit inside. So the telescope has been built in order for it to fit by folding it up. So I'll show an animation right here. And we mentioned earlier today the 7 minutes of terror that was associated with the Curiosity mission. So we decided to one-up that and go from 7 minutes of terror to 14 days of terror, because James Webb is going to be deploying while it's moving through space towards its final point, Lagrange point 2, L2, going around the sun. And it has about 200 different actuators on it, and each one of them, even though it has a redundancy system on it, if it breaks or something, then we have to think quick on our feet. We don't know what's going on. And it's not like we have a GoPro that's looking at this telescope that's deploying, telling us, okay, this is what's happening. The telescope can talk to us a little bit while it's doing all this. We get status updates, but we don't have an image of what's going on. So you can see in the video here, You have the big deployment that's going on, but you can also follow the trajectory of the telescope here. You have the moon right there, about 380,000 kilometers away from the Earth. And you have a countdown here. So you can see that the time is counting down pretty quickly. So this looks like it's moving pretty fast. When you think about, a rover landing on Mars and starting to deploy its things, its instruments, and taking a picture, it can take a while, but it doesn't necessarily take 14 days for that to happen. Whereas here, every movement is extremely slow, extremely deliberate. So you have the sun shield that is folding down, and it's going to, the tower with the mirror is going to come up, and you have the big sun shield that opens up. The sun shield is the size of a tennis court, so very, very large. And you can see that at this point, we're about 5 or 6 days in, so the mirror hasn't even unfolded at this point. And we are about twice the distance of the moon away. So the sun shield is coming unfurled. And you can see that it has 5 layers. The 5 layers on the sun shield are important to make sure that you're really effectively shielding the instruments and the mirror from the sun, but it's also in case that there is a micro debris or meteorite that comes in. There's 5 layers that can protect the telescope from that impact. You have the secondary mirror that comes down here. And you might notice how wonderfully gorgeous the telescope is. Again, it's an open concept telescope, which is the first of its kind. It's also the largest space telescope that has been made up until now. And you might notice that it is golden, which is not what we think of when we think of Hubble. So the mirror is an 18-segment mirror. All of the little hexagons inside of the mirror are made of beryllium, which is a metal that acts a lot like silica glass, but it is 5 times lighter and much more resistant. So one of the things you need to consider when you send something up into space is the fuel that you use to send it up. So the lighter what you're sending up, the better. So we want to make sure that the mirror is very, very resistant, but very, very light as well. So the 18 segments that make up the mirror are made of beryllium, and they're coated with gold because gold is what reflects infrared the best. You'll have aluminum, so the silver look of Hubble, because Hubble is a visible wavelength telescope, but gold is really the best thing for infrared, and it also makes it look way snazzier. And it makes great jewelry, like the necklace that I'm wearing right now, which is a little replica of the mirror. So I mentioned that this telescope, which again costs $10 billion, or will cost $10 billion at the end of everything, is not going to be repairable. So one of the reasons why there are multiple delays is because we need to do thorough testing. And the tests that we do on the telescope are meant to simulate the really extreme environments of rocket launch and also the extreme environment of space. So when you launch something up in a rocket, you are shaking it and you are making it endure acoustic waves that are several tens of times louder and more intense than a rock concert. So what we have to do is we have to ship this telescope into a giant vat. We have to shake it. We have to take all the air out of that giant testing vat so that it's exposed to vacuum, just like the vacuum of space. We have to subject it to extreme temperatures. So I have a video here that's going to show, it also shows you the scope and just how large this telescope is when you compare it to all the little ant engineers that are scurrying around it. So moving this around takes an enormous amount of effort. A lot of this work is being done in Northrop Grumman in California. And it really takes a lot of work, and one of the criticisms that came up after last year's most recent delay in the launch is that NASA had sort of stopped supervising the work a little bit more. But since then, I can confirm with all of the sort of insider meetings that I've attended that NASA has really undertaken the responsibility of testing a lot more now. So you can see that they're vibrating the telescope here. And unfortunately, when the telescope was first started as a project, they thought that it was going to be launched in 2008. And then we had several budget cuts that happened over 2010s and everything. And there were some delays there. But for a year now, the launch date hasn't moved from March 30th, 2021. And we're all very confident that that date is going to stick. So we just finished a very important phase in the testing, the spacecraft element. So the two parts of the telescope, the mirror and the instruments, and the spacecraft, which is the bottom part with the sun shield, they're separated and they've been tested separately. The spacecraft was the last thing to be tested, and it just finished its last round of testing, thermal vacuum, which is the temperature and the vacuum of space test. But now they're going to be reunited together, and now we're going to do the whole process again, shake the whole thing, but together as one piece, as it would be in space and inside the rocket. So why build an infrared telescope? We've had a lot of different infrared telescopes up into space. We have Spitzer and we had Herschel. Spitzer is actually on its final leg now. It's in its final year, but it's a much smaller telescope than the James Webb Space Telescope. And why do we want to study infrared light? Infrared can still have a lot of the beautiful value that we have in visible, but it allows us to see lots of different things in space that are basically invisible to us if we're just looking at optical wavelengths the way that Hubble was looking at. So some of the interesting elements that we can study in space that we can't using other wavelengths is, for one, planets. Planets glow quite brightly in the infrared, which is one of the reasons why we need to ship the Webb telescope so far away from Earth. So here you have a really gorgeous picture of Jupiter, the top of Jupiter, and you have the whirlpool storms on it. And it's an infrared image here from Juno, and you can see that it glows quite brightly in the infrared. If you go further than our own solar system, another thing that's very interesting that needs to be studied in the infrared is something called a protoplanetary disk. So these are baby solar systems that are being formed, essentially. And these are not only interesting in and of themselves, but they're also interesting if we want to know more about the formation of our own solar system. So we can try to make simulations about what happened billions of years ago in our own solar system, but that's sort of like a best guess. What we really want to do to compare those theoretical simulations is look at other solar systems that are being formed as analogs of our own solar system many billions of years ago. So this is one of the rare cases where you can actually take a direct image of what we call an exoplanet, a planet outside of our solar system, and in this case it's being formed. So the central star is being blocked here by a mask so that it doesn't outshine everything that's around it, and you have around the central star a disk of gas and dust, and you see a small planet that's being formed there. And this glows very, very brightly in the infrared specifically. So it helps us to study these exoplanets and these solar systems being formed, but in turn helps us understand the formation of our own solar system better. Something that I am particularly interested in as an extragalactic astronomer is studying galaxies, of course, and studying very, very old galaxies. And why is infrared interesting here, you might ask? Well, the very first galaxies shone very brightly in the ultraviolet and in the visible wavelength. But because of a phenomenon called redshift, which is the stretching of light due to the expansion of the universe, the light that was first emitted by these galaxies in the ultraviolet and the visible is infrared, has turned into infrared light once it reaches the Earth and the James Webb Space Telescope. So if you want to study the very first galaxies ever formed in the entire universe, you need to do it in the infrared. So one of the big components, one of the big scientific missions of Webb is to study these first galaxies ever formed using the infrared. One of the really important reasons also why we study infrared is because it allows us to pierce through dust that blocks a lot of the visible light if we're looking at like a Hubble image. So here you have an image of the Pillars of Creation, very, very iconic image, and everyone recognizes all of the blocked out light due to the dust, so that's what makes those pillars, those columns. If you were to instead look at exactly the same region of space in the infrared, you'll see that that region of space looks dramatically different. You can see, for one, loads more stars, and that's because the majority of stars are much smaller and dimmer and cooler than what is visible in the ultraviolet and in the visible. So here in the infrared, you see a plethora of smaller red stars that weren't very visible before. And you can also barely make out the pillars here because the infrared light has pierced through that dust. So in order to sort of look through these dusty regions, these star-forming regions, it's important to do it in infrared. So I mentioned that Webb has 4 scientific instruments. They're all infrared instruments, but they probe slightly different ranges of the infrared. 3 are near infrared, 1 is mid-infrared, and they all have different functions. And one of the 4 instruments, is actually a Canadian contribution. And it's sort of interesting. It's not a single instrument. It's sort of like a double instrument. It's called NIRISS. And it has a guiding camera on it that is used for every single observation that is made by the telescope. And it also has a scientific standalone instrument, which I'll talk about in just one moment. The other instruments are combinations of cameras or photometers or spectrographs. So you can take spectra or you can take images. A lot of the work that Webb will be doing is actually spectroscopy. And as one of the outreach scientists for Webb, that's going to be sort of an interesting challenge for me because the average person doesn't necessarily know what a spectrum is. And so we're trying to figure out all of these different techniques using something like a spectrographic or spectroscopic glasses or little diffraction lenses to try to explain to a 10-year-old kid, this is what a spectrum is, this is why it's important to study this in astronomy. So it'll be an interesting challenge, but I'm looking forward to trying to rise to the occasion. So the Canadian instrument was built by the Canadian Space Agency and was led by a researcher, René Doyon at the University of Montreal. He is an exoplanet hunter. And the main goal, really, of the NIRISS part of this instrument is to hunt for exoplanets. There's a lot of interesting spin-offs that we can do, like studying those very early galaxies that now shine in the infrared once the light reaches here. But really, the main goal of NIRISS is going to be to not only hunt for exoplanets, but probe the atmosphere of these exoplanets, try to figure out their composition, and perhaps find the first biosignature beyond Earth. I'm saying perhaps because after a lot of simulations, we're realizing that James Webb might have a hard time having the appropriate resolution to find these biosignatures. It'll be a great start, but I think the era of the extremely large telescopes that's coming up in the next decade will be a really good addition to the James Webb part of that puzzle. So there are 4 different missions, scientific missions for James Webb. One of them is to study alien worlds. So one of the components for that is studying exoplanets. And one of the ways that we can do that is using the NIRISS instrument that I mentioned, using something called transit spectroscopy. So here you have a very large star with a planet that will be passing in front of it. I think it's 2 planets that will be passing in front of it. And what we do with the NIRISS instrument is we study the light of the star that shines through the atmosphere of that planet. And whatever elements or molecules that are in that atmosphere will absorb some of the light from the star. And so we won't have spectral lines in emission, we will have spectral lines in absorption. And because we are getting pretty good at knowing what the spectrum of a star looks like, we can sort of do a subtraction and figure out what the elements in the atmosphere of the exoplanet are. So here in the animation, you can see the planet is going in front, and you can see a transit here. And as the planets go in front, depending on the size of the planet, depending on how fast they're going, which is related to how close they are to their star, you can get some information on them. And again, you're looking at the atmosphere of these stars. One of the really exciting targets for this specific project is going to be looking at the TRAPPIST-1 system. So for TRAPPIST-1, we have 7 exoplanets, which is already a very large number. It's the second most crowded exoplanet system. We found one that may have 8, but 7 is still a lot. And more importantly, out of these 7 exoplanets in the system, 3 or maybe even 4 are inside what we call the habitable zone. So the habitable zone is always a very contentious term that we use, I find, in presentations to the public, because it evokes all these images of there are aliens here and there are beaches and all these different things in life on these planets. But really, the habitable zone is strictly just the region, the distance away from the star where liquid water can exist. So now it opens up this big box of worms. What are the conditions for life? Is liquid water really essential? Can you live without it? Do you need it? Is just having liquid water proof enough that there's life? But we have to start somewhere, and we have to base our idea of what alien life could look like on the only type of life that we know of, which is the one on Earth. And for the most part, it requires water. So TRAPPIST-1 is going to be a very exciting target. We're going to be looking at a few different planets in the system. And again, what we're really interested in is probing the atmosphere of these planets. So here you can see a spectrum, and depending on these dips here, we can model these dips to identify which elements are inside of this the atmosphere of this exoplanet. And some of the really key molecules we're looking for are oxygen, water vapor, ozone, methane, so carbon dioxide. So if we can spot these, it'll be at least a good start to trying to find biosignatures somewhere. But biosignatures, if we do find some, will likely be something on the order of like a microbe. It won't necessarily be, little green men or ET. That's more like SETI's domain, I think, trying to find radio waves that show intelligent life. But we would be ecstatic if we found a biosignature that showed microbial alien life. We're also interested in studying alien worlds inside of our own solar system. And a really exciting target for Webb is Enceladus. So Enceladus became quite popular a few years ago when Cassini probed the cryovolcanoes, the sort of ice volcanoes on the surface of Enceladus. And inside you found interesting markers, not proof of life, but proof of possible food for life. So that means that we haven't found life, but we found some ingredients that shows that perhaps there's life. So Enceladus is a moon of Saturn. There's a liquid ocean, we think, under a crust of ice. And one of the only ways that we can probe what's going on under the surface is to look at the plumes coming out of these cryovolcanoes. There's a mission that's being talked about, the Europa Clipper, or the Europa Lander, which would potentially fly by or land on Europa, which is a pretty similar world, but a moon of Jupiter. And it would maybe, I'm not sure where we're at in terms of project status, but maybe it would try to drill a hole into the ocean. But Webb will take a less aggressive approach and just use its spectrograph to look at the plumes coming out of Enceladus to try to figure out what's going on under the surface in its liquid ocean. As I mentioned, we can also study the stellar life cycle and what's going on in the formation of stars and their planetary systems. Again, here, this is a baby solar system being formed. Another interesting type of star, but like a sort of in-between between stars and planets, that really requires infrared for us to study it, are called brown dwarfs. So brown dwarfs are objects that are not quite planets, not quite stars. A lot of people call them failed stars. I don't study brown dwarfs, but I have friends who study them, and they don't like that. It's very negative. So they call them like superplanets. It's a much more positive connotation, they find. So these brown dwarfs are several times larger than Jupiter, and they're massive enough that they have deuterium fusion inside their cores. So deuterium is heavy hydrogen, so it's not massive enough in order for nuclear fusion of hydrogen to be ignited inside of the core of the star. But it still manages to do deuterium for a while. So it's not quite a planet, not quite a star, and it's really important to study this sort of in-between object between stars and planets for us to understand the spectrum, because as we learned with the whole trying to categorize Pluto into one category or another, space doesn't really care about our neat categories. There's an entire spectrum of things. Things are not discretely placed in categories. So it's important to study these transitional objects to try to understand the mechanisms that happen, the physical processes happening inside these objects. One exciting project that is being led by an astronomer at Western University, actually, Professor Els Peters, is to study something called photodissociation regions. And this is essentially trying to study the effect of very, very massive stars that are blowing energy and wind into their environment, their dusty environment. So here you have the Orion Nebula, and you have here the Orion Bar, and that's a photon dissociation region. And so the energy that's being re-injected into the medium between the stars is actually having a chemical effect on the molecules there. So the infrared light would be the best one to study these different processes that are happening inside of these really intense stellar regions where massive stars are emitting energy. And of course, everyone loves black holes, so we can't leave black holes out. Studying black holes is a very important component of Webb. It's going to be studying black holes at different mass ranges. So we have stellar black holes, which is sort of like the classical black hole that you think of, but it will also be studying supermassive black holes, which are found at the center of galaxies. So now again, my favorite subject, studying galaxies, we want to study them through time. So the universe has changed appearance quite a bit over time. The very early universe was much more active. There were many more galaxies that were colliding together. Stars were forming in galaxies at a much faster rate. The universe is relatively quiet now compared to what was going on in the very early times. And so we've been able to probe pretty deep into the past of the universe. You all know that looking farther back is like looking through time, right? Like astronomy is a time machine. Okay, I'm going to take the nodding that I see as a yes. So if you look further and further back in space, you're also looking further and further back through time because light has a finite speed. So Hubble did a pretty good job trying to look back at about 500 million years after the universe started, after the Big Bang, but James Webb thinks it can do better than that, and it's going to try to push to 200 to 300 million years after the Big Bang. So it would be a little bit risky to say that we're going to be looking at the first light ever emitted by something in the Big Bang, but we can safely say that we're going to be looking at some of the first galaxies that are being formed inside of the universe. And again, to do this, it's useful to look in the infrared. But even if we're looking at the infrared, trying to look at something that's very, very far away, even with a 6.5 meter telescope, can be a little bit difficult. It can be quite harrowing. So we have to use different techniques, different sort of tricks of the trade to try to make these objects easier to study. And one of the things that we can do is use something called gravitational lensing. So we know that mass curves space-time in general, but around us, we all have an effect on the space-time around us, but we're not very heavy, so we don't really see that effect. As we get to larger and larger objects, we see larger and larger gravitational effects. So the Earth has an effect on us, the Sun has an effect on all the other planets. If you get to massive enough objects, you start seeing really, really dramatic curves in space-time, such that light that's being emitted by an object behind a very massive object is going to be completely warped. So here you have a bunch of different galaxies that are in a cluster together, and while that's a lot of mass, the part that you can't see is actually really what's important. What all these galaxies are embedded in are a really massive dark matter halo, which is about 10 times more massive than the galaxy that you can see themselves. So there's a whole lot of mass going on here, and there are far away distant galaxies that are emitting light behind this massive cluster, but because this cluster is warping space-time, when the light reaches us, it's completely warped. So we have a really distant red galaxy here that looks like a normal galaxy if you're looking at it just normally. But because we have this mass that's warping space-time, it's all elongated here. And we have a few other ones there. So we have little warps all around that are due to this. But it doesn't only warp the image of these galaxies, it can also magnify the light rays such that the galaxies that were very dim and very far away can find themselves magnified multiple times, even 10-fold over. So it makes them a lot easier to look at. So here's a diagram, just to reiterate. You have a big mass here, something that's emitted far away, and so the light is curving around this big mass. And so when everything is perfectly aligned, you can get something really beautiful like an Einstein ring. So in this case, you have a single massive galaxy that is causing gravitational lensing of one distant, perfectly aligned galaxy. And so you have almost a perfect ring that shows up behind it. So just to make sure that everyone is on board and everyone understands what we're talking about, one last animation. You can see the faraway galaxy, it's emitting. There's a cluster in between, and this is the image that we end up seeing here. So you can have a full Einstein ring, partial rings. You can have something like a cross where you have the image of the galaxy that's replicated multiple times, but like as discrete points. And trying to disentangle all of that is a nightmare and requires a lot of computational power, but you get a 2-for-1 in this case, because not only can you study the very distant galaxies, which are now more visible, but you can also map out the distribution of dark matter that warped space-time. So you get a little 2-for-1, but you have to work pretty hard for it. Finally, the last scientific mission of Webb is to study the very early universe. So as I mentioned, we're trying to probe very, very far back here. At some point, we hit something about 300,000 years after the Big Bang, which is sort of like a stopping point, unfortunately. Before then, the entire universe was an opaque plasma, so no light could come out. Photons couldn't escape from this really, really dense era of the universe. So that's sort of a wall, but we keep pushing further and further back to try to reach that wall and try to see the light of that wall, which would be the first light ever seen in the universe. So I want to make sure that you have a good coffee break and that we have some time for questions. So I sort of want to end with why Webb is important for Canada specifically. And it's especially important now because the whole world, I think, as we saw in Catherine's talk today, that the whole world is sort of being swept up in this like renewal of space exploration and wanting to go to space and everything. And NASA's going to do it, Europe is going to do it. You have other superpowers like China and India that are starting to jump in. And Canada, which was the 3rd country to ever go into space, is now classified 8th after Luxembourg in terms of space funding per capita. So it's a little bit scary, and we're sort of losing our footing. And we have a lot of interesting expertise. We have a lot of know-how, a lot of really great scientists and engineers and industry that can do a lot of great technological development. And we have international partners that are knocking at our door who are hoping to have us join their missions. And one example of that is WFIRST. So WFIRST is the next flagship mission from NASA after James Webb will launch, because it will launch in 2021. And WFIRST will be focusing mostly on figuring out what dark energy is. So good luck to them, because wow. And also studying a lot of exoplanets in general. And Canada was supposed to be part of WFIRST. And we had a lot of great contribution to give for this mission. But unfortunately, I think it was a year and a half ago, NASA came and knocked at our door and said, okay, it's great that you're part of this mission, but we need a solid financial commitment from you now. And the CSA looked in its coffers and its vault and realized it didn't have the money to join the mission. And then NASA said, that's too bad, Canada, we're going to miss you, but this train has to keep moving. So the door is not completely shut, but the door is closing more and more on WFIRST and the missions after it. James Webb is an incredible chance for Canada to get on board with space astronomy, and I really hope that I and all of my colleagues can make Canada feel part of this mission. But it's already running quite late in terms of getting on board the next mission, because James Webb is something that Canada got involved in the late 90s. Like in 1999 is when it really started. René Doyon, who's the PI of James Webb in Canada, joined the mission in 2001. And we're launching in 2021. So that's 20 years. So the time to get on board with the mission after James Webb, really it's 10 years ago, but we can't go back in time unless we're looking far away in the universe. So we really need to sort of get on board with the next big thing. So I mentioned WFIRST, and another really cool mission that's coming up is called LUVOIR, which is going to be an optical telescope, but really massive. Another open concept, very similar to James Webb. There are different configurations. It might be on the order of 10 to 15 meters. Instead of the 2.4 of Hubble. But LUVOIR is it's starting now. It's one of 4 flagship missions of NASA that are being considered, but those decisions are going to be made soon. And if Canada wants to be part of it, we have to make that decision now. So astronomers in Canada are in a bit of a tricky position now because the Lunar Gateway just got a huge chunk of money, and that's very exciting. But at the same time, that's not space astronomy. That's not science in this kind of sense. And so when we try to, tell people, be that politician or the public, telling them we need to fund space astronomy, they're like, oh, but the moon just got all this money. And it's part of our job as educators to try to help them understand the different branches of astronomy, because ideally there would be room for everyone, but it needs to be a diversified model. And so I think this is where collaborations between astronomers and the RASC and other outreach institutions is really essential, because there aren't astronomers everywhere in Canada. And there are lots of you that are all over the place doing such great work. So one of the things that I'm hoping to do as the outreach scientist for James Webb is to develop material that we can pass on to you and develop workshops where we can, give you all this material, all of this knowledge, so you can become ambassadors for space astronomy and James Webb, so that hopefully Canada isn't left out of this narrative going forward. So I look forward to collaborating with all of you working on this kind of project. Thank you. Just in time for the coffee break. Thank you.
I couldn't do any better.
All right.
Do you want to take a few questions?
Yeah, I can. Yeah, there's time, I think.
Any questions?
I'll repeat the question. So the question is, when can we expect the first image and results? And that's an excellent question, because a lot of people are going to be really pounding at our door saying, hey, this costs $10 billion. Where the heck is our first image? But it's going to take about 6 months for the phase of the mission called commissioning, for all the instruments to be tested, make sure everything is running well. We're going to be taking images during that period of time. We're sort of investigating the best way to release the first images, but likely it won't be until about 6 months. But what we really want to do, and what I'm pushing for as much as possible in my role as outreach scientist, is for transparency during that commissioning phase, so that everyone feels like they're part of this adventure. They know what's going on. Oh, they just focused the mirror, and now instead of seeing like 18 blurry things, they see one sharp thing. And creating products and making posts on social media so that people are aware of what's going on, instead of like radio silence for 6 months, because that's totally unacceptable. But the results, the first images will start coming out about 6 months, and then about a year after launch, we can start seeing scientific results lightly. Yeah.
Thank you. Thank you for your presentation, Dr. Ouellette. How does the telescope get transported from the States to French Guiana?
On a boat. And you better hope nothing happens to the boat. Yeah.
Yeah, great talk, Nathalie. Thank you. Going back to the deployment of the GWST, was it ever considered, everything that's at stake and all the risk, was it ever considered to have a dummy or a proof of concept mission where they send up dummy components just to see if the whole thing works?
I think in terms of sending it really far away, other infrared telescopes like Herschel have been to L2 before. So there have been proof of concepts in terms of telescopes sent to L2, and those have been successful missions. It didn't have they were closed off telescopes with tubes, so it didn't have necessarily the complexity of this whole thing unfolding. But this whole thing unfolding is one of the reasons why this is so expensive. So the dummy would end up costing, I don't know, maybe billions of dollars as well. And then people would be like, why is this $12 billion? And so it would be difficult to start testing on that level. But we have proofs of concept in terms of other telescopes that have been sent to L2.
Thanks again.
Oh, thank you.
Here, we have to show your...
Okay. I'm excited to see what it is.
Yeah.
Oh, the Oort cloud.
Oort cloud.